Hello, my name's Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary, and this is my module on single symbol detection. In our match filter module, we talked about how the digital communications receiver is basically divided into two functional blocks, the demodulator and the detector. The demodulator, which was essentially our match filter, its purpose was to take the received analog signal and convert it into a received signal vector at a rate of 1 sample per symbol, and to do it in such a way as to maximize the signal quality, which we expressed in terms of signal to noise ratio. Now our job is to take that received signal sample, or the received signal vector, into the demodulator, into the detector, and to try and guess what information was being sent to us by the transmitter. And we want to do this in as reliable a way as possible. And so much of our discussion in this module will be relating to how to determine our received information bits such that we minimize the probability of error. One of the key assumptions that we're going to make in this module is that the information bits that we're receiving are memoryless. Or in other words, they are independent of each other such that our current information bit has no statistical relationship with the bits that came before it and the bits that are coming after it. And so in this memoryless scenario, we can show that we minimize the overall probability of error by making individual decisions on individual symbols, ignoring the symbols that came before us and ignoring all the symbols that come after us. It is worth noting, however, that there are some important cases where memory does exist in our information stream. Sometimes memory can be added by our channel, and sometimes we add it intentionally. So for the channel case, if we have a dispersive channel such that our transmitted signal is smeared in time, so that it overlaps with the symbol that comes after it, we get what's known as intersymbol interference, where the symbol that came before us is actually interfering with our current symbol. There's then a relationship between our received symbol and the ones that came before it, and so we need to take those other symbols into account in order to minimize our overall probability of error. A case where we add memory on purpose is when we use error correction codes, so that rather than transmitting individual information bits, we use information bits to select a code word, and then there is a relationship between the bits of those code words that we can use to improve our overall probability of error, but we have to be then making our decisions on a code word level rather than on an individual bit level. But anyway, for the purposes of this module, we will be assuming that all the bits in our information sequence are independent. So to start off our discussion, it's easiest for us when dealing with the detector to operate in terms of signal vectors rather than complex envelope signals. So we're going to assume a received signal vector R that has a length equal to the number of basis functions of our signal. And if we wanted to sort of sum up the whole sort of detection problem, we would say that based on our received signal vector R, which is the only information we have about our transmitted signal, the purpose of the detector is to guess the transmitted signal vector SM using a technique that minimizes the overall probability of error. And the way that we do this is to start with Bayes' theorem. Now, there's a couple different forms of Bayes' theorem. There's the more familiar all probability Bayes' theorem that we generally introduce in undergraduate probability classes. The form of Bayes' theorem that we're going to take will be a mixture of probability values and probability density functions, or PDFs. And so on the left-hand side of our expression, we have what's known as the posteriori probability, which is the probability that SM was transmitted given that we've received a certain signal vector R. And so we basically want to choose the transmitted signal vector that was most likely to have been transmitted given the information that we have in R. And so minimizing the probability of error is the same thing as trying to maximize the posteriori probability. We want to choose the signal vector that was most likely to have been transmitted. And if we do that, then we minimize the overall probability of error. And so our objective is to maximize the posteriori probability. Now, let's take a look at what we have on the right-hand side of the Bayes theorem equation. The first thing we have is something that's known as the likelihood function. And this is a PDF. It's not a probability value, it's a PDF. And it's the probability density function of the received signal vector R, given that we assume that a certain signal vector Sm was transmitted. And this likelihood function can be determined ahead of time based on knowledge of the behavior of our system and the noise in our system. And we'll see this a little bit more in detail later on when we look at particularly the additive white Gaussian noise case. But you can think of the likelihood function as a probability density function that we would generate in the lab by essentially transmitting the same signal vector over and over again. Let's say we choose signal vector S1, we feed signal vector S1 into our transmitter over and over and over again, and then we look at the received signal vector R that we have at the receiver, given that we're sending the same signal vector S1. Well, you know, if there's noise in our system, we're not always going to receive the same value, even though we're transmitting the same signal vector every time. Our received signal vector is going to wander around a little bit. And so you can think of the likelihood function as basically a histogram where we feed in a known signal and then we create a histogram of the variation that we see at the output of our receiver due to noise, right? And so we do that for, so we create a likelihood function for signal vector S1. We create another likelihood function for signal vector S2, S3, and so on until we've got likelihood functions for all of our possible transmitted signal vectors. Now, you can think of this conceptually as having separate functions for every signal vector. Often we can express this as a single equation where the transmitted signal vector is just a parameter. The third element we have in our Bayes theorem expression is another PDF, and it's the distribution of the received vector R. Now, students sometimes get confused about the difference between the likelihood function and this second PDF, which is just the received signal vector distribution. The likelihood function is a PDF where we fix the transmitted signal vector to be just one signal vector. FR, the PDF that we have in our denominator here, is the PDF if we look at how the received signal vector changes for all values of noise and for all values of transmitted signal vector. And so FR is basically the total variation we see in R for all possible signal vectors. So how would we determine FR in the lab? Basically, we would just set our transmitter to transmit randomly, you know, all the different possible signal vectors, and we would look at all the possible received signal vectors over all of these transmitted symbols and all these noise values and create one giant sort of overall PDF. So it's not a function of transmitted signal vectors because we're basically averaging over all possible ones. The final term that we have is actually a probability term. It's not a PDF, and it's just the probability. It's called the transmitted symbol a priori probability, and it's just the probability that a particular signal vector was transmitted. In most cases, as we're going to see later on, we assume that all signal vectors are equally likely to be transmitted, in which case this probability is just equal to 1 over m, where m is our number of signal vectors. And so basically, our problem that we're going to tackle in the coming slides will be to choose the transmitted signal vector Sm with the maximum posteriori probability, which is the left-hand side of our Bayes theorem equation. And we're going to manipulate the right-hand side of the Bayes theorem equation in order to find a way to select the signal vector that's as efficient as possible. Now, generally speaking, a lot of the area of digital communications is really quite independent of sort of the underlying hardware that implements our algorithms. We don't often think a lot about the actual implementation of the hardware and how difficult our algorithms are. However, there is an obligation for physical layer designers to make things as simple as possible for the underlying systems that are implementing our techniques, particularly because modern communication systems have to go so fast. So as a designer, you potentially will be working on wired systems, wireless systems that are going 10 gigabits per second, 100 gigabits per second. And remember that if you're feeding bits through your communication system that fast, that means that your detector has to be making 100 billion decisions per second, which is a real challenge, particularly when you look at the clock rates of kind of modern processors. And so it's incumbent on us as designers to make our detectors as simple as possible. So actually, much of what we're going to be doing in this module will be attempting to simplify our detection rules so they are as computationally efficient as possible. Now, if we look at our previous slide, we have a Bayes theorem expression, and we're trying to choose the signal vector that maximizes the left-hand side of that expression, the posterior probability. And we are going to be manipulating the right-hand side of the equation in order to do that. And so on the right-hand side of the equation, we had 3 terms. We had our likelihood function, we had our distribution of R, and we had the a priori probabilities. What I want to do on this slide is to pull out as many terms as possible that don't affect our final decision. The reason why this is possible is that a detection decision is fundamentally a relative comparison, right? So we want to choose the transmitted signal vector with the maximum posteriori probability. And so if we removed a term from that calculation that was common, such that all of a sudden those posteriori probabilities were divided by 2, it still wouldn't affect the decision that we make in our detector. As long as we make linear or monotonic changes to our detection metrics, we will always still consistently choose the same transmitted signal vector. And so what we're going to do is we're going to remove the terms on the right-hand side of the Bayes theorem equation that we don't need. And so if you remember, on our denominator, we had our distribution of our received signal vector. However, this distribution is a function only of the received signal vector R and not the transmitted signal vector Sm. This is basically a PDF equation that's the overall distribution for received signal vector values, and it's the same for all transmitted signals. And so we can pull it out of the Bayes theorem equation and not affect the relative comparison of posteriori probabilities. Same thing for the a priori probability term Ps of m. That was the term that was here. If we assume that all of our transmitted signal vectors are equally likely, then this probability value is equal to 1 over m for all of our signal vectors, and we can remove it as well because it's the same for all of our posteriori probability values. And so what we end up doing is we remove this term, we remove this term, and we are left with our posteriori probability being proportional to our likelihood function. And so rather than calculating the exact value of posteriori probability and then doing a relative comparison with those probability values, instead, since we know that the R distribution and the a priori probability don't really affect our relative comparison, what we do instead is we ignore those two terms that I've crossed out, and we instead just choose the transmitted signal vector that maximizes our likelihood function. And this, when we do this, it's something that's known as maximum likelihood detection. And so we ignore those other terms, we maximize our likelihood function, and that ends up being the transmitted signal vector choice that minimizes our overall probability of error. So it turns out that we now have to add a few more assumptions to our discussion. Our likelihood function, as we talked about a couple of slides ago, the likelihood function can be generated experimentally by fixing the transmitted signal vector to be a constant value and then looking at the variation that we get in our received signal vector, basically due to the additive noise in the system. But you can also include interference and other factors as well. But the most common set of detection rules are for the additive white Gaussian noise channel. And so this is the this is the likelihood function that we get when we send a particular signal vector through a channel where that signal vector is corrupted by additive white Gaussian noise. And the Gaussian noise causes the variation in our received signal vector, and not surprisingly, we then end up using the Gaussian distribution as part of our likelihood function. But let me sort of show you this by going through this step by step. And so again, this first point, if we fix our transmitted signal vector Sm, the only variation at the output of our match filter is due to additive noise, right? Because we're transmitting the same signal vector over and over again. Now, our likelihood function is a vector PDF, right? So it's the distribution of all the samples in our received signal vector R, given that a particular signal vector was transmitted. However, if the noise is white, that means that the noise corrupting each value of our signal vector is independent. And so the overall sort of vector joint distribution is equal to the product of, and this p should be in, this little p should be an f. These should all be f's, that's a typo. The joint distribution is equal to the product of the PDFs, or the distributions of the individual sample values in our signal vector. And so assuming we have k basis functions, we would have k PDFs being multiplied together in our joint PDF. And so if we go further and assume that the noise is Gaussian, then if we transmit a particular signal vector value and our received signal vector value is corrupted by zero mean additive white Gaussian noise, then the PDF of that signal vector value is just the Gaussian PDF, right? And so we have the familiar Gaussian PDF form over here, where the mean of our received signal sample is just equal to the signal that we're transmitting, right? And that's because this is zero mean additive Gaussian noise. The mean of the received signal just assumes the signal level that we happen to be transmitting. And so this is the PDF for the individual signal samples. And so if we take this expression and we plug it back in here where we multiply a whole bunch of these guys together. The overall likelihood function, and again that p should be an f, I fixed that, is just equal to this Gaussian term where we have a summation of terms in the exponential. And so this is the likelihood function for any communication system in the additive white Gaussian noise channel. And so you can actually use this equation to perform maximum likelihood detection such that you minimize your overall probability of error. How would you do this? Well, let's consider a simple example. Let's consider a binary PAM case where our first signal vector, S1 is equal to, let's say, +3, and our second signal vector, S2, is equal to -3. Our receive signal vector that we observe at the output of our matched filter is then equal to 2.4. And n naught, let's say, is known, right? Because we do a thermal noise calculation on our receiver, and so we know what level of thermal noise to expect. So how do we perform maximum likelihood detection? Well, we calculate two likelihood values. The first thing we do is we figure out the likelihood value when we plug in our receive signal vector r, which is just equal to 2.4, and our transmitted signal vector S1, which is just equal to +3. And of course, in this particular case, k is equal to 1, right? Because we have only one basis function. And so if we go over here to our likelihood equation, we've got a value rk, which is equal to 2.4. We've got a value of s, which is equal to +3. We've got a value of n naught, which we know, and we calculate an actual numerical value for our likelihood function. And let's say it's equal to 7. We can then do exactly the same thing for the second signal vector. So we've got our likelihood function. We have the same value for r, and then we have our signal vector S2. And so we go over to this exact same equation. We plug in the same noise value, n naught. We plug in the same value for r, 2.4, but then we plug in the value of -3 for s. And then we calculate a second likelihood function, and let's say that value is 3. I'm making these values up. And so comparing those two, 7 is larger than 3, and so the first signal vector S1 has a larger likelihood function value, and so we would choose S1 as the one that was most likely transmitted. That's no surprise, right? Because the value of 2.4 is very close to 3 and it's very far away from -3. And so we can perform this calculation, and this is maximum likelihood detection, and we minimize our overall probability of error. However, just looking at this example, you might have noticed that this is a fairly complicated calculation. We've got an exponential expression, which is computationally expensive. We've got a square root here. And for those of you that are following really, really closely, you might have noticed that we're doing a couple of unnecessary calculations. So for example, the value for n naught is the same for both signal vector S1 and S2, and shouldn't affect the relative comparison of our likelihood functions. And so even though this is true maximum likelihood detection, there still are some savings that we can make if we simplify this expression further. So the first thing that we do to simplify the likelihood expression even further is we take the natural log of it. And this may not seem intuitive at first, but this is a very, very common way to simplify decision metrics that utilize the Gaussian distribution, right? So the Gaussian distribution has that exponential term in there, and of course the natural log is the inverse of the exponential distribution. And when you take the natural log, you essentially eliminate the exponential operator from your decision metric. Since the natural log is a monotonic function, it also does not affect the relative comparison between likelihood values. And so we take the natural log of our expression, and on the right-hand side, we have a term that's a function of the noise value. Then we have essentially the argument to our exponential. Now, again, continuing in the spirit of removing things that we don't need, this first term is the same for all signal vector values, and so we can get rid of it. Over here, 1 over n naught, the same for all signal vector values, so we can get rid of it as well. And so if we want to maximize the likelihood function, or the log of the likelihood function, we basically end up trying to find the signal vector that minimizes the term that I'm circling now. However, if you look at the term that I've circled, that's nothing more than the squared distance between the received signal vector values and the particular transmitted signal vector that we're considering. So maximizing the log of your likelihood function is the same as minimizing the distance between the received signal vector r and a particular transmitted signal vector. And so this ends up giving us an extremely simple and extremely intuitive way of performing maximum likelihood detection. We basically just pick the received signal vector, or we basically just pick the transmitted signal vector that's closest to the received signal vector value. And when I teach this class at the undergraduate level, I have in the past skipped all of this probability stuff and just asked the class and said, okay, you know, you've got a received signal vector value r, you've got all these possible transmitted signal vectors, which one do you choose? And invariably, they immediately come up with the answer that, well, you just choose the one that's closest, right? And this intuitive idea is, you know, what we arrive at when we go through all of the probability work with starting with Bayes' expression. And so it's a very nice, very sort of intuitive result. Minimum distance detection also has a very nice sort of graphical interpretation. This is the picture that I typically show my undergraduate students when we're to start off the minimum distance discussion. So if you've got a 1 or 2 or, you know, 3-dimensional received signal vector, you can draw a signal vector diagram. And on that signal vector diagram, you can put all of your possible transmitted signal vectors as well as the location of your received signal vector. And so on this slide, I show a QPSK example where we've got 4 possible transmitted signal vectors, and our received signal vector r, because of the additive noise that's corrupting it, doesn't exactly match any one of them. And so what's the most logical thing to do here? What's your most logical choice? Well, you can just determine the distance between r and S1, r and S4, r and S3, and r and S2. We're of course closest to S1, and so we choose S1 as the most likely transmitted signal vector. And it makes intuitive sense, and we've seen from our previous slides that this is the choice that also minimizes our overall probability of error, maximizes our posteriori probabilities, and corresponds to our maximum likelihood detection choice. So now, even though minimum distance detection seems fairly simple and intuitive, and it is, we can continue our quest for greater computational efficiency even further. The squared Euclidean distance does require a squaring operation, which is a multiplication. And so to simplify things even further, we can expand out the summation of squares. And when we do that, we get the expression here. And we can express that also in terms of our vector form, where we've got the squared norm of r minus 2 times the cross product between r and a particular signal vector plus the squared norm of the signal vector. Now, this term, the squared norm of r, is common for all of our distance expressions, so we don't have to calculate it. We can get rid of it. And if we then take the negative of what we've got left, we get something that people refer to as the correlation metric. And the correlation metric is just equal to twice the cross product of r and the signal vector minus the squared norm of the signal vector, which of course is just the energy per symbol of signal m. And in the case, so that means in the case of PSK, for example, where all the signals have the same energy per symbol, we can get rid of that guy as well. And then we end up just with the cross product between R and S. However, if you're working with QAM, where the symbols have different energies, you have to include this energy per symbol value back into your decision, because it basically compensates for any bias you get due to unequal symbol energies. But this is basically as simple as you can get, and it still gives us the maximum likelihood decision that minimizes our overall probability of error.